This problem is actually not too tough. It's asking us what the standard cell potential is for a voltaic cell based on this reaction. Well, in order to do this, what we need to do is separate it out into its semi-half reactions by figuring out what's oxidized, what's reduced. Let's go ahead and throw this thing down. So I've got 3 irons, and each of them has a 2+ charge being converted into 3 irons that have a 0 charge. How do I do that? Well, this iron's going from being positive to being 0, which means that it's becoming more and more negative, which means that it's gaining electrons. So if I gain electrons, that's reduction. So this is my reduction step. In order to balance out the charge, I've got total 6+ charge on the left. I'm going to have to add 6 electrons on the left, and that should do it. And we can see that this iron is gaining these electrons. How about the other reaction? I've got chromium, 2 of them, being transformed into 2 chromium 3+ cations. Well, this is going from chromium 0 to chromium 3+, which means it's becoming more positive, which means it's losing electrons. Losing electrons is oxidation, so this is my oxidation step. Where do I throw those electrons down? Well, I'm going to have to throw them down over here. So I've got 6 electrons right there. Conveniently, I think these actually balance out, at least 6 electrons in the reduction, 6 electrons in the oxidation. I think we're good to go. So, yeah. Anyway, so that's the overall process that I'm looking at. Now, in order to determine the standard cell potential for this, all I need to do is remember that the standard cell potential for this is going to be equal to the cell potential of reduction, so equals cell potential of reduction minus the cell potential of oxidation. So if I can find actual cell potentials or EMFs for each of these steps, I can throw them into this equation, hip hop ram, done. We can do that, of course, by using the table that I supplied in the lecture that I'll show you momentarily. Let's begin by noting we're trying to look for some kind of reaction that has electrons and iron 2+ on one side and then iron 0 on the other. Electrons and iron 2+ on one side, iron 0 on the other. Let's take a look at the table. Do you see any of these that have electrons on one side and iron 2+ on one side and then iron 0 on the other? Yeah, you see that the electron potential there is negative 0.44. So we'll go ahead and write that down, negative 0.44. Now one thing that's interesting about these is the stoichiometry doesn't matter. It's still negative 0.44 if I have 3's in front of these, if I have 1's in front of these, if I have zillions in front of these. Totally the same. Now let's look at the oxidation. The oxidation, I've got chromium, and I've got Cr3+ and some electrons on the right side. Looking back at our table here, do you see any of these reactions that have got chromium 3+ and some electrons on one side, and then chromium 0 on the other? Yeah, you can see it's this top one here with a number of negative 0.74. So now let's see if we can find the overall electron potential here for the reaction. I have to take the number for the reduction. The reduction is the one up top. That's going to be negative 0.440. I have to subtract from it that for the oxidation. The oxidation is a negative 0.74. So I'm taking this and subtracting from it a negative number, which is the same thing as adding it. You do that in your calculator and get the final answer, and whatever that final answer is, well, it happens to be right.